Add the period, right? So we have to think about what the period is. So good review, because we haven't done a lot of trig stuff in a while. If you have a sine or cosine graph, the period is 2 pi over b. If you have a tangent, the formula would be, of course, pi over b. So if I'm looking at this one to determine its period, its tangent, so it would be pi over 2. The coefficient in front of theta would be 2. I'm going to think of this as something over 6, just to make the math a little bit easier. So of course, 3 pi over 6. And I'm going to basically keep adding the period until we get to something beyond 2 pi, and then we'll have all the solutions of where it's crossing the pole at. So let's just go ahead and do that part now. I have pi over 6, show all of what I want to show, plus the period is going to give me 4 pi over 6. That's already a solution, so I'm not going to include it. 4 pi over 6 plus the period, that would be 7 pi over 6. I can keep going, plus another 3, 10 pi over 6. And again, I can reduce these. Not going to add it again, because the next one's going to be 13 pi over 6, which is over 12 pi over 6, which is over 2 pi. So far we have 1, 2, 3, 4, 5, 6 answers. Doing this next one, 2 pi over 6 plus 3 gives me 5 pi over 6. That's already an answer, so I'm not going to just repeat that one over and over again. Then for this last one, 5 plus 3, 8 pi over 6. Could reduce it if I want to. And then adding it again, 8, 9, 10, 11. 11 pi over 6. I can see that's almost 2 pi, so I'm not going to add the period again. So if I'm talking about this polar graph, really what's a big idea is how many times is this graph going through the pole between 0 and 2 pi. And we just count the solutions. It crosses pole 8 times. On that interval from 0 to 2 pi. Why is it going to be important for us to determine where a graph crosses the pole? Ultimately, calculus-wise, like a lot of interesting things happen when the graph is going through the pole. We know a lot of these graphs are going to be very I don't know, they make circles, they make things that look like roses, they make things that are like spirals. They're going to go through the pole a lot. And we will see when we start doing things like area between curves, that pole does play a special role. The other reason why I want to do this is all of those 8 points that we found, those are all angle measurements where it's crossing the pole. Those actually have a direct calculus meaning as well. So something that is new, something that's not from pre-calculus. So here's the graph. That's the one that we just found. That's r is equal to 3 minus the tangent squared of 2 theta. It's that graph you see in red. All of those dotted lines you see are the angles representing the solutions that we found. So for example, I'm going to kind of go back to it. The smallest solution we had was like pi over 6. The next one we had like a pi over 3. That's what that one is reducing to. All of those solutions where it crossed the pole are in many ways going to be considered tangents at the pole. So like this dotted line, that was theta is equal to pi over 6. This one, theta is equal to pi over 3. These lines do have 2 names. For example, that green dotted line, I could have also described as theta is equal to 7 pi over 6. But all those are going to have special characteristics. And the special characteristics, the way we're going to define this is actually a theorem. And it basically states if theta is equal to k is a solution to r of theta is equal to 0, then the line or lines theta equal to k are tangent to the curve at the pole. Putting this in kind of everyday terms of what this basically means, When I say the equation r of theta is equal to 0, this is basically when the curve crosses the pole. Those values, those angle measurements of where it's crossing the pole, are also tangent lines on the graph. So notice it's a little bit different way of thinking about tangents. We don't have to find a derivative. We don't have to do like y minus y1 is equal to m times x minus x1. The solutions to the equation r is equal to 0 are themselves lines that are forming tangent lines. You can kind of see why that is. Could prove the theorem, but it's not the easiest one to prove, but you can kind of see how the curve bends. Where I have all those dotted lines, they really do kind of form tangents to that little curve shape that we have going on. So that's one thing that I want to do. That's going to be something that's new. Questions on anything that I've done so far? One thing that I would want to add to this, just make sure I'm kind of being thorough. If I just take one of these tangent lines, like this is the polar equation. We know that theta is equal to pi over 6 is a straight line through the origin. If you had to convert this into rectangular form, what would you basically have to go through? What process, or what would you do to both sides to put it into rectangular form? Take the tangent of both sides. And then you can kind of see if you take the tangent of both sides, well, what's tangent of theta? Y over x. The tangent of pi over 6, that's 1 over the square root of 3. So that line, theta equals pi over 6 in rectangular form, is y equals a line with a slope of 1 over root 3, and then x, and of course the y-intercept is 0. So sometimes it might ask you to find, hey, what's the tangent line for the pole? Set it equal to 0. Your solutions are lines, and you can always convert it into rectangular form. Next part that I wanted to review, and this is going to be the last kind of pre-calc topic, and that's going to be the question, find the points x comma y at which these curves intersect. Where in calculus do we often talk about intersection points? Often we're doing areas. You can kind of see where this will expand into the calculus. If I want to find where two curves are intersecting, what's basically the algebra I have to do? So set them equal to each other and solve. So I would have 4 sine of theta is equal to 4 minus 4 sine of theta. Solve it. 8 sine of theta is equal to 4. So the sine of theta is equal to 1/2. When is sine equal to 1/2? I think about the interval from 0 to 2 pi. That's going to happen at pi over 6 and 5 pi over 6. Do you want to talk about how this question is kind of worded? It is asking you to find the points x comma y. That is going to be rectangular coordinates, the x and the y. Right now we just have the theta, so we are going to have to kind of finish this up and do some conversions. We have one point at theta is equal to pi over 6. How do I find the r value that goes with that theta? Plug it in. Does it matter which one I plug it into? No, they're intersecting, so I'm just going to choose the easier one. 4 sine of pi over 6, which is 1/2, so we get 2. So we have one intersection point at r comma theta. That is the polar coordinate. How would I go from the polar coordinate into the rectangular coordinate? R cosine, R sine. So doing my conversions, R cosine of theta, R sine of theta. Cosine of pi over 6 is root 3 over 2, so I have the square root of 3 comma 2 times 1/2 or 1. So I have the polar version of the coordinate, which is sometimes used for us. I also have the rectangular coordinate, which is more familiar, but also can be useful in some other contexts as well. And then I can go ahead and repeat that for the other point. Hopefully you can kind of see it's just going to be the same value in the second quadrant. And again, where I got that 2 from, if theta is equal to 5 pi over 6, plug it into one of them. 4 sine of pi over 6 is 2. That's the polar coordinate. Putting it as a rectangular coordinate, our cosine of theta, our sine of theta. Cosine is negative in that quadrant, sine is still positive. So we have two kind of points of intersection. I do want to say some other ways you could have done this one. So this is something that we could easily do by hand. Some students do like having a visual or like a way to kind of test their answer or to kind of check their answer. And one neat fact that we have kind of with polar graphs and polar coordinates. So when I have these two equations, I'm going to write it up here to the side. When I say r is equal to 4 sine of theta and r is equal to 4 minus 4 sine of theta, that's a set of polar coordinates. You can graph them, you could visually see their intersection points, but they are directly related to those two graphs and just replacing the r and the theta with y and x. Now, to be clear, they're not the same graphs, they're just related. But if you were to graph these two equations, y is equal to 4 sine of x and y is equal to 4 minus 4 sine of x, if you were to graph both of those and find their intersection points, they wouldn't have the same coordinates, but they would have the same angle. So the angles that the rectangular graphs cross would be the same as when those polar graphs cross. And that can be like a way to check your answer to make sure you found like all the intersection points. I did want to show you another thing. So intersection points, we know we do a lot with area. Polar graphs are already weird because like they just kind of go around and around the pole. We know that sometimes like a certain point can have multiple names to it. And so that is the algebra. When we want to find two intersection points, we do set them equal to each other. But I do want to show you the graph to this problem. There's the graph of those two equations. I see the two intersection points we found. We found one in the first quadrant at root 3, 1. We found one in the second quadrant at negative root 3, 1. But looking at that graph visually, which intersection point is missing?
The pole.
The pole. And that's going to be something that pretty much happens frequently. The pole is not going to show up often when you set two equations equal to each other. So you will notice that often you have to check to make sure that the graph goes through the pole or doesn't go through the pole. So I'm actually going to expand the definition when finding the intersection of polar graphs. There's going to be three things that you want to do. The first thing is going to be the obvious one. You're going to set your two equations equal to 0, not equal to 0. Set the two equations equal to each other and solve. That's typically going to give you some intersection points. But then you also need to check to see if both cross the pole. And you don't have to make this difficult for yourself. So like, yes, you could do it the long way, set it equal to 0, and then solve for r. Or just plug in a value or kind of think to yourself, is there going to be an angle you can plug in to make it equal to 0? But that's basically what you're going to check for. This last one, part of me hesitates to show you this, but I think it's going to look really confusing, and some of y'all are going to get scared. And I'll explain it after I write it down. But there is a third possibility of when they can intersect, and that third possibility is basically where one of them is crossing at an angle with a positive r, but the other one is on the opposite side, but with a negative r. And I know that looks really confusing. Short version of this is often the way they word problems on the AP exam and the way they present problems. That third option is probably not going to be something you have to deal with. I'm just going to go ahead and give you the math just because I think it is important, but there are two identities that are useful for that. And that sine is the same thing as sine on the opposite side of the circle, but changing the sign. Same thing with cosine. Cosine is equal to its opposite when you're on the other side of the circle. I say all this, and again, I don't want that to look more confusing than it actually is. On the AP exam, and so I'll be the same as well, you will often be given the graph. And what that means is, like, if you have the graph, you can easily see how many intersection points you have, and when it comes down to it, you can just kind of guess and check. Which sounds obnoxious. I know a lot of you just like, hey, just give me something to solve. The short version of it, though, is like, they're going to give you problems that you can do easily and efficiently. Those identities you're not going to have to know for the AP exam. So honestly, if that third one and those identities are confusing, just know that the ones we do, you can figure it out without them. Big idea, though, that I want you to get from this is really those first two. When you need to find the intersection point, yes, you're going to set them equal to each other, but you always have to go through and check to see if they both happen to go through the hole. So what I wanted to finish up with, looking at the time, I got a little bit more time left, and then I'll stop. I did want to go ahead and just do the first part of polar functions in calculus, so I can save all that area stuff for next week, and we can do kind of the easier parts of it today. And so when we do polar functions with calculus, we are going to treat those polar functions like parametric functions. It's actually going to be easiest if you think of them that way. In fact, when you think about it, when we first learned polar graphs, we learned them in the parametric unit. Like, they really are tied together. So when I say a polar function, that's something in the form of r of theta is equal to some sort of polar equation. Like, that's a polar graph. Where does that r show up at? It's technically a parametric equation in disguise, because we know x is equal to r cosine of theta, y is equal to r sine of theta, and when I say that r there, that's literally the same r as what your polar equation is. So often when we're doing calculus with polar functions, we're just going to convert it into its parametric mode, looking at the x's and the y's. And then I will say, when it comes to the calculus that we do with polar functions, there's mainly just two things that we have to do with them. We'll find the derivative, dy dx, and do all the stuff that you can do with the derivative. And then we also do area between curves, which I think is a little bit more difficult. That's what we're going to do next week. Often you're not going to find the second derivative. In fact, it's not required for AP calculus to find the second derivative of a polar function. And I think that makes sense when you think about these graphs are always curved anyway, so it's kind of weird to talk about concavity. So often we'll just talk about the first derivative, all the stuff you can do with the first derivative, and then area. And I wanted to go ahead and finish today up by doing the derivative, and that's where I'll kind of conclude today's notes. So how do we find the derivative of a polar function? Very similar to how we found the derivative of a parametric one. So let's review how we did a parametric one. What we did earlier this week, when we were doing it in parametric form, and we needed to find the dy dx, what general formula did we think for this as? dy dt over dx dt, correct? And again, I think visually you can kind of see how that works. The dt's cancel out, and you just have the dy over dx, dy dx, the first derivative. We're going to do the same thing with polar functions. Dy dx is still going to represent the slope of a tangent line, so we are going to have to think about it in terms of y and x. What's the independent variable, though, for a polar function? R. The other one, theta, right? So we plug in the theta to get the r. So how do we think about dy dx in polar form? Its formula, dy d theta over dx d theta. Thinking about what that represents, d theta means you're taking the derivative with respect to theta. So we're going to think about it as d theta of y over d theta of what? Of the x. And here is where your conversions come from. Well, in polar to parametric form, what is y the same thing as? R times the sine of theta. And then we think about the x's. What's the formula we use to find x? R times the cosine of theta. Finding the derivative of a polar function is not difficult. It's really more tedious because when we see that r times sine and r times cosine, what derivative rule is going to show up when you're finding the derivative of these? Probably the product rule and probably the product rule twice. So when's the first reason we would use a tangent, when was the first time we would find a derivative? The first application we did was finding a tangent line. So let's do this problem. This is where I'm going to kind of end at today. I want to be able to write the equation of the line tangent to the graph of r is equal to tangent of theta when theta is equal to pi over 4. Same with parametrics. When we do tangent lines, we're always just going to go back and write it as our traditional rectangular version of a tangent line. We're not going to write like the tangent line in polar form or anything like that. You're going to leave it in rectangular form. So we know that when we're trying to find a tangent line, we have to have two things. We have to have the point, and then we also have to have the slope. So let's find the point first, and then we'll do the slope that has the derivative. Well, we want to find this tangent line when theta is equal to pi over 4. How do I find the r that goes with that pi over 4? Yep. Just plug it in. So we have, what is the r? R is equal to the tangent. Try to choose one that's a little bit easier. Tangent of pi over 4 is just 1. So what's the coordinate of the point of tangency? R, comma, theta. That is your point. But that is your point in polar form. To write the equation of a tangent line, it needs to be a y1 and an x1. It needs to be in rectangular form. So let's go ahead and convert this. I have r times the cosine of theta, comma, r times the sine of theta. So the coordinate we're using, cosine of pi over 4, 1 over root 2 or root 2 over 2. I don't care which one you use. Same thing for the sine. So I have my coordinate. And then to finish it up, if I'm writing the tangent line, we have to have the point, and then we also have to have the slope. Where's the slope going to come from? It's going to come from dy dx. So again, let's review that formula of where it's going to come from. This is a polar function, so we're going to think about it as dy d theta over dx d theta. Well, when I say dy d theta, that means take the derivative with respect to theta of y, and then divide it by the derivative with respect to theta of your x. And we just have to plug it in. Well, the formula we use for y is r sine of theta. Can't plug things in yet before we take the derivative. What value or what expression are we using for r? Tangent of theta. So there's the formula, r sine of theta. What is r? R is the tangent of theta times the sine of theta. That's my expression for y. Then do the same thing for x. X is r cosine of theta. There's my r, there is my cosine of theta. Now, when you find the derivative, it often has to use the product rule, unless you're simplifying. So I would kind of check to see if I can simplify just to save me some time. Are we going to be able to simplify tangent times sine nicely? Is anything going to cancel, basically? No, so it's not worth rewriting. Tangent is sine over cosine, still going to be the product rule no matter which way I rewrite it. But tangent times tangent times cosine does simplify. What is that going to simplify to? Sine. Would you have to simplify it? No, but it does save you from doing the product rule 1 time instead of 2 times. So taking the derivative now, we're going to do the derivative of y with respect to theta, and then the derivative of x with respect to theta. So here's my derivative of y. Product rule. First times the derivative of the second plus the second times the derivative of the first. The derivative of tangent is secant squared. And in that denominator, we said tangent times cosine is sine. Again, if you didn't simplify, you're doing the product rule. We did. The derivative of sine is cosine. Could simplify, but this is going to be pretty easy to plug in. We're trying to find the tangent line at theta is equal to pi over 4. So I can go ahead and just plug that in pretty easily. Tangent of pi over 4 is 1. Cosine 1 over root 2. The sine of it, 1 over root 2. Secant, I think reciprocal of cosine. That's going to be root 2. Squaring it is going to be just 2. And then the cosine of pi over 4, 1 over root 2. What's going to happen to all those 1 over root 2's? If we want to simplify it nicely. Or maybe we're not going to simplify it because we don't see it.
Oh, wait, no, you flip the 1 over root 2 on the bottom.
Really isn't that what one whole number is actually going to be simplified to?
Wait,
Try again. Factor out the 1 over root 2. Oh, I guess we'll do it. It's Friday.
We're in calculus, not algebra, come on.
Oh, wait.
3, yeah, easy, easy. So that would be my slope. That is the slope of that polar function at pi over 4. So what is my tangent line? My tangent line is y minus that y coordinate in rectangular form is equal to the slope times x minus the x coordinate in rectangular form. And there is my tangent line. Again, what's the hard part? None of it. What's the tedious part? Finding the first derivative of a polar function. You have to remember to rewrite it. Y is our sine of theta, x is our cosine of theta. And often what makes that complicated is you're going to have the product rule, sometimes once, sometimes twice. Maybe no times if it simplifies nicely, but definitely probably the product rule.
Well, clearly the hard part is the algebra.
Or the hard part, apparently factoring out of 1 over root 2 and simplifying, yeah. But any questions on that one? All right, so that's where I'm going to stop at today. On Monday, when we return, we're going to talk about how we find polar area of, like, saying, like, find the area of a portion of a cardioid, or maybe the area between two curves, or the area of a rose curve, or the area, like, between two loops of a limacon. That's where we're headed. That's kind of where knowing polar graphs and knowing calculus is going to be blended together. At this point, here's the assignments you have left for this unit. Just kind of making sure you are caught up and where you need to be. So parametric homeworks for numbers 1, 2, and 3. Once you finish those, if you just want to test your own knowledge, there is an optional quiz, old quiz, posted in the answer key folder that just covers parametrics. If I had more time, I probably would have given you all a quiz over parametrics. Maybe you're glad we didn't have time. At this point, you have homework 4. That was going to be the polars from pre-calculus. And then you can also start the final homework already, the polar functions and calculus. And again, you can just start that since we haven't really talked about the areas yet. Looking ahead, not officially assigning it, but there will be, of course, the briefcase binder. And then your Unit 11 test is going to be on Thursday, the 22nd. And then after that, we have basically 7 class days to get ready for the AP exam. So at this point, y'all can go ahead and get started on that homework. You have the remainder of here to get some stuff done, also to ask questions.